Exercise 525 is asking you to find a plane of symmetry in each of the following molecules. And at first that might seem really random. What difference does a plane of symmetry make? But if a molecule has symmetry, then it has two sides that are exactly the same. And if it has two sides that are the same, then the molecule as a whole is not chiral. So remember that chirality is a phenomenon of geometry. It's not specific to chemistry. Anything that has four different sides comes in two versions, a left-handed version and a right-handed version. It doesn't have to be an atom. It could be your hands, which are chiral, or your feet, your shoes, or gloves. Anything that has four different sides is chiral. Now, we've been seeing a lot of chiral atoms that are bonded to four different things, but you could also zoom out and think about a whole molecule. You can think about the whole molecule as having four different sides. And if a molecule has four different sides, then that molecule would be chiral. Now normally, if a molecule has a chiral center, then it will have four different sides, so that molecules that have chiral centers tend to be chiral molecules, but that's not always the case. If a molecule has a chiral center, so if a molecule has a chiral center, but also has a plane of symmetry, then that molecule has a special name. It's called a Meso compound. And it's special because it has a chiral center, so you have to think about chirality in the small term, the chirality of specific atoms, but as a whole, the molecule is not chiral, it's achiral. So that's what a Meso compound is. And the difference that makes, it says, what difference does it make if a molecule that contains chiral atoms possesses a plane of symmetry? The difference that it makes is that the molecule as a whole is not chiral if there's a plane of symmetry, and so the molecule as a whole does not come in two different versions. So here we can get some practice just recognizing the planes of symmetry. In this first molecule, if you take a flat plane that's in line with your screen, and if you take that and you cut the molecule right down the middle, half of the methyl group will be on one side, half of the methyl group will be on the other, half of the chlorine will be on one side, half of the chlorine will be on the other, half of the bromine will be on one side, half of the bromine on the other. So we're letting that plane down so that it slices those two atoms. In that case, you have a plane of symmetry right there. And so we sort of have this plane of symmetry that cuts through the molecule across this bond. Now, it's not up and down, it's a vertical plane. So it's not horizontally cutting this. That's not symmetrical because the chlorine doesn't match the bromine. It's vertically cutting it. Vertically cutting it, so from the top straight down through those middle two carbons. And that's the symmetry there. In this next one, you can see there's a symmetry if we slice it right down the middle. Everything on the top is on the bottom, so you have symmetry there. Notice that in this molecule, you have a chiral center. You have one there, you have there. We've talked a lot about 1,2-dimethyl cyclohexane and how there are chiral centers there. But in this particular molecule, the molecule as a whole is not chiral because it has that plane of symmetry. And so this is an example of a Meso compound. Same here, we have two chiral centers in this next molecule. They're both chiral, but you can find a plane of symmetry down the middle here. Everything on the right and left of that molecule is the same. And so that molecule as a whole is not chiral, it's achiral, it's a Meso compound. You could see a plane of symmetry, vertical plane of symmetry right here. Everything on the right and left is the same. So even though you have chiral centers, the molecule as a whole is not chiral because the right side and the left side are the same because of that plane of symmetry. So the molecule doesn't have 4 different sides. And so the molecule as a whole doesn't come in 2 different versions, even though you have chiral centers in the molecule. So that's a meso compound. For this next one, you have a couple chiral centers. Each of these are chiral centers. You're looking at this bicyclic molecule from the side. If you take a plane of symmetry, so like a standing page, and you cut it through in between those 2 bonds, through the middle, in between, then you'll see that it goes right in between there and out through the other side. On the left and right of that vertical plane of symmetry, you'd have the same thing on both sides. And so that even is a meso compound, again, because it has at least 1 chiral center, but it also has a plane of symmetry. So you have chirality to think about on a small scale, on the atomic scale, but on the molecular scale, the molecule as a whole is not chiral. In this next one, you have a plane of symmetry that kind of goes through the middle of this. So if you imagine a plane sort of going back through the middle, so that it kind of goes up through there. On the right and left of that plane, you have the same stuff. And so because you have that plane, the chiral centers that are here, and we have 2 of them, those chiral centers don't make the molecule as a whole chiral. So this is a meso compound because these are both meso compounds, because the molecule has a chiral center, at least 1. Both of these molecules happen to have 2. They have chiral centers, but the molecule as a whole is not chiral because of a plane of symmetry. In that special scenario where you have a chiral center, at least 1 chiral center, and symmetry, gives you this meso compound, and it's significant. The difference it makes, it's significant because the difference it makes is that the molecule as a whole only comes in 1 version, even though there are chiral centers in the molecule. So that is the concept behind this one.